Hello and welcome again to Physics Made Simple. This is Net Force and Free Body Diagram Made Simple by Dr. Eid. Okay, so with forces, let's quickly recap that we have two types of forces. We have balanced forces and unbalanced forces. When we talk about balanced forces, so we can focus on objects that remain at rest, and we know that object at rest will remain at rest, and objects in motion remain in motion at a constant velocity, assuming that there's no friction if the object is pushed forward or air resistant if the object is being dropped down. When we talk about unbalanced forces, we always think about objects that are accelerating, changing speed and acceleration. So some formulas to remember when we talk about forces is that force is always in newtons, mass is in kilograms, acceleration, the unit is meters per second square, gravity, we will use 10 newtons, even though gravity is 9.8 meters per second square, but we will use 10 just to make our life easier, so 10 newtons. Weight, we will use it in newtons, even though there's a difference between mass and weight. Mass is in kilograms, weight it's when we add the gravity pull to it. Force of gravity, we always remember that this is anything that will pull downward. Force of lift is anything that will pull upward. Force of thrust is anything that will push forward. Force of resistance is anything that will have a resistance. This also, we can refer to it with friction, because it could be friction that's pushing back, or air resistance, that's air resistance as something is falling down. For a formula for the net force, always remember that it's mass times acceleration, and we can move those around, and this is Newton's second law. Force of gravity or weight is mass times gravity. We just said that, and we always, like I said, are going to be using 10 newtons for that. Again, when we talk about the mass, we have the force divided by the acceleration, and if it's the object that's going downwards, we said acceleration downward, we are going to be using 10 meters per second or 10 newtons. These are some of the formulas that we've already mentioned. The net force is the sum of all forces acting on an object, and it could be the force of thrust, force of friction, force of lift, resistance, air resistance, and whatnot. And we add or subtract, because once you have one of them will be forward, the other one is backwards, and so forth and so on. Free body diagram, I'll explain a little bit more on the next slide. When we have a direct relationship, it is when force increases, that means acceleration is going to increase, and that is common sense. When I push on something, I know that it's going to accelerate in one direction. So as I push, the more I push, the more the object is going to accelerate. And the inverse relationship is, we have an inverse relationship when we have a greater mass. So the higher the mass, the more I have to push. And the higher the mass, the less the acceleration is going to be. It's not going to be as quick if we have a smaller mass. So if I go ahead and I throw a ping pong ball, it's gonna be a lot faster than if I throw a golf ball. So simply, force, the definitions for force. Force is a push or pull, and in a minute I will show you, we have a PhET simulation that allows us to actually play around with forces and see how they behave. when we add and subtract of these forces, or same goes with mass. If I increase mass, what happens to the acceleration, and if I decrease mass, what happens to the acceleration. And this is basically understanding the direct and the inverse relationship better. Force can be applied in many directions at the same time, and this is the free body diagram that we will depict, because when I push, I know that in the opposite direction there's at least the force of friction from whatever surface that object is sitting on. And if I pull on something, same goes with the pulling. Again, net force is the combination of all forces applied on the object, and it is measured in newtons. So for example, if you look at that little box, we have a push force forward of 20 newtons. The resistance backward due to the surface is 10 newtons. So we can subtract those two, 20 newtons minus 10 newtons, and the net force acting on the object will be 10 newtons and will be to the right. Therefore, this brings us to the fact that the net force will always have a magnitude, which is a number, and a direction. And it will tell us that that object is going to have this much magnitude, 10 newtons, to the right. It's going to be going to the right. So as I push forward, the table underneath is pushing backwards on me 10 newtons. If it was pushing 20, then I won't be able to move it, and I would have to increase the force. But since I'm moving it forward at 20 newtons and the table is pushing back at 10 newtons, so 20 minus 10, so this force applied is moving the box to the right at 10 newtons. One of the things that I always use in my class is PhET simulations. And if you go on PhET simulations and you type in the force, you have a lot of things that actually come up. And if you click on it, then it will bring up an actual simulation that you can play around with and see what happens when you add force on one side, and at the same time, if you increase the mass, what happens? If you decrease the mass, what happens? Again, PhET simulation is a lot of fun, and it will help you understand the inverse relationship better, because that's basically what a lot of people struggle with. Again, direct relationship is when one increases, the other one increases. So if I increase my force, the acceleration is going to increase. And inverse relationship is if I increase the mass, it's heavier now, then my acceleration is going to decrease. So here's an example of what a free body diagram looks like. First of all, the definition is it's an illustration that is used in physics to show the magnitude and the direction of all forces acting on an object. And notice that if the object is that box, we see that there are forces in 4 different directions. At least the first thing that we could think of is the F of G, or the gravitational force acting on the object. Also, in the opposite direction, there's something called the normal force, which is the total opposite and equal to the force of gravity, unless we have another force acting on it, like, for example, air resistance, or the tension if it's hung by any item that pulls it up. For example, in an elevator, you have tension due to a rope that is pulling all that weight, or the elevator weight, upwards. The other thing you have to remember is the force of friction, which, if we have a car, the force of friction is going to be all the pushback from the asphalt, from the street, from the driveway. If we're talking about something that is being pushed on a table, it's the table surface. If it's a very smooth surface, it's not going to be as high. But if it's very rough, then the force of friction is going to slow down that acceleration so much, because it's going to be pushing backwards against the force you apply. Again, the last one is the force that you apply on the object. This brings us to practicing these problems. This is one of the easiest problems you will see. One of the things I want you to notice is the heads of the arrows give you the direction and the magnitude. A lot of times you see that those arrows are clearly showing you that one is larger than the other one, therefore showing you and giving you a hint of the direction of the higher force that you're going to end up with. So let's go ahead and try some of these problems and see if we can hopefully learn how to work with that, as well as our great force is equal to mass times acceleration formula. So this one, we have a force of gravity downward of 100. The opposite direction is normal force of 100. So 100 minus 100 is going to be 0 newtons. And then we have a force that you are applying forward of 20 newtons. And guess what? You have a force of friction from the surface of the object that you are pushing on that is equal to the force you're applying. So 20 minus 20 is 0 newtons. So the net force in this case is going to be 0 newtons. Here's another simple problem. Let's go ahead and determine the magnitude and the direction of the net force acting on this object. We have an up and a down force. Force of gravity is 150, equal to 150, which is the normal force. So 150 minus 150, we know that that object is not going up or down because it's 0 newtons in those directions. The only other thing that we have an applied force of 60 newtons. Do we see a friction, force of friction? No, we don't. Therefore, we're not going to be subtracting anything from that. That being said, we'll say 150 minus 150 is equal to 0 newtons. The net force acting on the object is 60 newtons to the right. Here's another problem with multiple forces acting on it. Again, we see that we have a force of gravity equal to normal force. So 200 minus 200 is going to be equal to 0. Now let's look at the other ones. We have a force applied of 120 newtons. Let's say this is another person holding on with you and pushing forward with you and adding their force of 60 newtons. And then we have a force of friction from the top of or the surface of the item that's sitting on of 8 newtons. So what we do is we say, okay, 120 forward plus 60 forward, then we have 180 forward. Now we have to subtract the 80 backwards from the 180, and that is due to friction, and we will end up with the sum of all forces, 100 newtons, and this is going to be moving to the right. Here's another example where we can actually fill in some more blanks. We have a problem showing that we have an applied force to the right of 240 newtons and a force of friction backwards of 80 newtons. So we can go ahead and figure out that the net force acting on this object is 240 minus 80, which is 160 newtons to the right. We know that the object is accelerating to the right at 4 meters per second square using the net force, which is 160, and the acceleration of 4 meters per second square. We can go ahead and rearrange our formula to state that the mass is equal to force divided by the acceleration, which is 160 divided by 4, and that gives us the mass of the object of 40 kilograms. Now, we're not done yet because we need to figure out the force of gravity downward. Force of gravity downward is equal to the mass times g, and assuming that the force of gravity is 10 newtons, we are going to multiply 40 kilograms times 10, and that's going to give us 400 newtons downward. And we know that we have an equal and opposite force of normal force. This gives us an answer for the normal force to be 400 newtons. Let's look at another problem with some missing blanks. In this problem, we have a force, a normal force upward of 160 newtons, and missing a force downward. But we have the mass. Using the mass, we know that the F of G downward is 10. We can go ahead and multiply 8 times 10, and that gives us the force downward, or the F of force of gravity using the mass is going to be 80 newtons, or 8 times 10, which is 80 newtons. That being said, we can go ahead and figure out the net force acting on this object, because it seems like we only have an upward and a downward force. 160 minus 80, that gives us a net force of 80 newtons upwards. This means that this object is being pulled upwards. And it could be an elevator. Can we figure out what the acceleration, or at what acceleration is this object being pulled upward? Sure, we can go ahead and rearrange the formula that says the mass is equal to, the acceleration is equal to the force divided by the mass, and that's 80 divided by 8, and that gives us 10 meters per second squared. Here's another problem, and this one we have more information to go ahead and figure out. We have an object that is being pushed and pulled at the same rate, or the force forward is equal to the force backwards, which is 20 minus 20, that gives you 0. And also, we have a normal force of 100 newtons upwards, but we don't know what the force downwards is. But we have the mass. We can go ahead and say, okay, 12 kilograms times 10, that gives us 120 newtons downwards. Then we can go ahead and figure out the net force acting on this object. We say 120 minus 100 newtons, and that gives us 20 newtons downwards. So this object is speeding or accelerating downwards at 20 newtons. How do I figure out the acceleration? We rearrange the force formula, and that gives us the acceleration is equal to the net force divided by the mass, which is 20 divided by 12, and that gives us 1.67 meters per second square. One of the quickest reviews you can do is something as simple as push and pull and ranking different objects, or the net force of different objects, forwards or backwards, negative or positive. So if we look at these, we can go ahead and start with the first one. A is 1 kilogram. We have a force forward and a force backwards, 3 newtons minus 1 newtons, that's 2 newtons to the right. The second one, or B, we have 3 plus 1. They're both going in the same direction. We do not have a friction force or a backward force, so 3 plus 1 is equal to 4 newtons to the right. The next one, both of these are to the left. We're going to go ahead, since we are ranking from negative to positive, we are going to use those as a negative direction. So 3 plus 1 is 4. They're going in the opposite direction, so that's a negative 4, or negative 4 newtons, or 4 newtons to the left. D, we only have one force backwards, which is negative 2 newtons, or 2 newtons to the left. E, we have 2 newtons plus 2 newtons, or 2 people pushing backwards, and or pulling backwards. We can say 2 plus 2 is equal to negative 4 newtons, or 2 newtons to the left. F, we have 2 newtons forward, 2 newtons backwards. They cancel each other. We have 0 newtons. G, there are no forces acting on the object, but we can say this object is actually 5 kilogram times 10. We can say 50 newtons downwards, or the object is just sitting and not moving anywhere. H, 2 newtons to the right, and I, you have 3 newtons to the left plus 2 newtons to the right. We have a negative 1, or negative 1 newtons to backwards, or 1 newtons to the left. That being said, we can go ahead and rank them. We take a look at all of these numbers, and we rank them from the most negative, which is the highest negative number to the most positive. I hope this helps. Please, if you have any questions, go ahead and drop some questions in the comments. If you have any concerns or any suggestions of some problems that you would like for me to work on, please let me know or email me. Thank you very much. Have a good day.